All right, so the second fundamental theorem we're going to talk about is when we don't have constants for the upper limit. So we are still dealing with f of x is going to equal an integral, but it's going to go from x to a, where my upper limit is a function of x. And inside here, we're going to use a different variable. We're just going to go ahead and use t, only because t is one of those things and one of the variables we're going to use very, very often. So then my function inside is going to be f of t dt. Now, we still have to be on a closed interval, and x must be in between a and b. And as before, f must be continuous, and it has to be on that closed interval from a to b. So what does all of that mean? It means that f of x is equal to the derivative with respect to x of the integral from x to a of f of t dt. So let's go ahead and look at an example with this. So let's say I have dx of the integral going from x to 1 of sine squared of t dt. So according to this second fundamental theorem, what is this saying? Don't overthink it too much. It just means the derivative with respect to x of the antiderivative, which is doing the reverse of each other. So that just equals the sine squared of x. So for another question, if I have the dx of the integral from 5 to x of the square root of t squared plus 1 dt. Now we've got to be careful, because in order to use the second fundamental theorem, this must be where x is. I absolutely have to have the upper limit being the function of x. So what I do with that is and this is one of the rules that we've talked about before, just put it as an aside. Recall that if I go from b to a of f of x, that is equal to minus the integral from a to b of f of x. So what I do with this is I just switch this around, and then that equals negative dx of the integral from x to 5 of the square root of t squared plus 1 dt. So that is just all equal to negative square root of x squared plus 1. We're going to do one more, but this time we're going to use a chain rule. So this time we're going to have dx of the integral from x squared to 0 of the cosine of t squared dt. Now again, the upper limit is not x, but it's a function of x. So therefore the function that we have to differentiate is a composite function, which means that we need the channel. So we go ahead and rewrite this. So now instead of having x squared, let that be u. So if u is equal to x squared, then the derivative of u is equal to 2x. I take the derivative with respect to u from u to 0 of the cosine of t squared dt, but I would have to multiply that times u prime. So all of that gives me cosine of u squared times u prime, which would give us cosine of x squared times 2x, or all of it is equal to 2x cosine of x to the 4th power.